Okay, here we go. Regents Review number 6. Here are the solutions. Hopefully this will help you. Let's just look at this little classroom here. We have a couple of different types of triangles, and then we have a student over there on the right raising his hand. All right. Number 1. Point Q is on MN such that MQ to QN equals 2 to 3. So we have a 2 to 3 ratio here. So you can see here in our little picture of the marbles, the ratio of green to red is 2 to 3. There's 2 pieces the same size, and then there's 3 pieces of the same size. Or in this case, they kind of look like marbles, so we'll go with that. So for every 2 green marbles, there's 3 red marbles. So that's what we're looking at here. So we want to come over to our graph, and we want to graph M and N. So M is at 3, 5. And then N is at 8, negative 5. Okay, so that's where our coordinates are. Now I'm going to attempt to draw a straight line, although the attempt, not too bad, but not too good either. But anyway, that's my line, and this is M, and this is N. And I want to break this up into 5 equal pieces because 2 to 3 ratio is 5 equal pieces. All right. So I'm going to do this graphically, which means I'm going to draw a right triangle. Okay. And I'm going to count each side. So there's 5 pieces here and 10 pieces here. Now since I want to divide the segment into 5 equal pieces, I'm going to divide both of those by 5. So here I get 1 and here I get 2. So starting from M, I'm going to go down 2 and then over 1. And then down 2 and over 1, down 2 and over 1, and I'm going to keep on doing that until I get back to N. All right, so I have 2 pieces, and then I have 3 pieces, right? 1, 2, and then 1, 2, 3. So that means that this point right here is Q. So that would be 1, 2, 3, 4, 5, 1. So Q is at 5, 1. Okay, let's go on to number 2. Number 2 says that we have this diagram here, and it's an isosceles triangle where AB is equal to BC. Well, if those are equal, I know that my angles are also equal, right? My opposite angles. So it also says that all of those segments in there are angle bisectors, which means that these 2 angles are equal, and these 2 angles are equal. And since they're equal to each other as well, all 4 angles are equal to each other. So if angle BAC is equal to 50 degrees, that means each of these is equal to 25 degrees. Because remember what an angle bisector does, it divides the segment into 2 equal or congruent pieces, angles. All right, we're asked to find angle AXC. So if you look at this triangle here, right, because there's lots of triangles in this picture, but this triangle here and all the other triangles, the sum of the angles have to add up to 180 degrees. So I know that 25 plus 25 plus angle AXC has to be equal to 180 degrees. So that would be 50 degrees plus angle AXC equals 180, and then subtract 50 from both sides, and I get that angle AXC is equal to 130 degrees. All right, on to number 3. All right, so we have this diagram here, and as soon as we see this picture, remember with the right triangle, we have a right angle here, and then we have an altitude, so we have the right angle here. We should be thinking geometric mean. Okay, so it gives us that CA is 12 and AD is 8, which means that this CD part must be 4 because 4 plus 8 has to be equal to the whole hypotenuse, which is 12. And we're looking for BC. Well, I know that the geometric mean is the leg. I'm going to use the leg theorem. And the leg is the geometric mean between the segment it's touching, which would be 4, and the whole hypotenuse, which would be 12. I'm going to cross multiply, and I get x squared is equal to 48. Take the square root of both sides, and I get x is equal to, and then that breaks down into 16 times 3, which is 4 square root 3. And then that would be my answer. Now, another way of doing this instead of reciting the geometric mean is to know that the leg is the geometric mean, which I already said, but this is in a different kind of notation because it's more formula instead of memorizing the actual theorem. The leg goes there, and then the segment that it touches and the whole hypotenuse, knowing that this is leg 1, this is the whole hypotenuse, and this is segment 1. And for that matter, this is segment 2 and leg 2, and this is the altitude. Okay, so 4 radical 3 is our answer. Number 4. In the diagram, we have these vertices A, B, C, and they're graphed for us. What is the slope of the altitude from A to BC? Well, here's BC, and BC, we want to draw an altitude from A. Well, what is an altitude? Remember, an altitude is the segment drawn from a vertex perpendicular to the opposite side. So it's going to be something like that. Now, on the coordinate plane, we always have to think, well, if I'm on the coordinate plane, what do I know about perpendicular lines? That's right, they're perpendicular, so that means they are negative reciprocal slopes. So, if I can find the slope of BC, the negative reciprocal slope would be the slope of the altitude. So I have the coordinates of B and C up here, so I'm just going to use those for the slope formula, the difference of y's over the difference of x's. So that would be 3 minus 1 over 7 minus 2, which is equal to 2/5. So the perpendicular slope, or the slope of the altitude, would be negative 5 over 2. And that is our answer. All right, one more. Rigid motions. So in the diagram, we see that ABC and XYZ are graphed. Using the properties of rigid motions, explain why the triangle ABC is congruent to triangle XYZ. So first, let's always map out. A goes to X, so A is going to go down here. That would be where A prime is. B goes to Y, and C goes to Z. So we want to figure out what kind of a rigid motion this is. So one way of doing that is to look at, oops, did that the wrong way. To look at the movement from A to B. So A to B goes this way. Sorry about that. Okay, so it's going this way, which is in a clockwise direction. Well, AB over here is also going or continuing to go in a clockwise direction. So we don't have a line reflection. If you notice, if you drew a line between all of these and their corresponding parts, oops, well, you can't really see it the way I'm drawing it. It's a lot harder than you think on this thing. But anyway, The origin would be the center of dilation. It's the intersection of all of those segments. Okay, so when you go from the image to the pre-image, you can see that they're all going to pass through that point. Okay, I think I'm just making things worse. What do you think? Okay, anyway, so this is a rotation of 180 degrees about the origin. Now, since rotations are rigid motions, and remember what that means, the size stays the same, the shape stays the same. So because they're rigid motions, that means that AB is going to map onto XY, and BC will map onto YZ, and AC will map onto XZ. Since they're all mapping onto each other, that means that they would be equal to each other. So AB, since it's mapped onto XY, is equal to XY or congruent to XY. They're the same length. And BC is going to be congruent to YZ, and AC, since it's mapping onto XZ, they're going to be congruent. So by side-side-side congruence theorem, these two triangles are in fact congruent. Okay, hope you do well on your quiz, and I will see you next time. Or you'll hear me next time. I guess I won't really see you.